introducing Ryan Rosario to talk about sentiment at Facebook with some of their data. For the quick rundown on Ryan's bio, he's a quant engineer at Facebook working on machine learning and natural language processing. Before Facebook, he used to work down in Los Angeles near me at doing machine learning and NLP involving real-time bidding. He holds a PhD in stats and MS in CS from UCLA. And Ryan's been coding in Python since 2005 when he started using it for web crawling and web graph mining. He's a recovering R user, though he's still a fan most of the time. We'll see if we can pull him or keep him on our side for the rest of the day. So with no further ado, Ryan.
Thank you. Thank you for coming today. Today I'm going to be talking about some experiments and proof of concept work that we've done here at Facebook around sentiment analysis. So the outline of my talk is basically I'm going to spend some time talking a little bit about sentiment analysis and current approaches, and then I'll start talking about approaches that we've tried and our current approach, and then I'll talk about the Python ecosystem and how we use it for sentiment analysis. I have a little bit of code that I want to show. It's very short because Scikit-learn makes this very easy. But there's a lot of infrastructure stuff that goes into this as well. Every 2 months at Facebook, we host a hackathon. And sometimes these hackathons have themes. Sometimes we're free to do whatever we would like for a hackathon project. And about a month after leaving boot camp, I decided to, I've been working on NLP stuff, and I decided, well, what if we tried to do some sentiment analysis with some text? So that was my hackathon project. And it ended up getting pretty good results on using NLTK, and we decided to end up using this as my full-time project for now, at least. So without further ado, I'll just jump into this. So sentiment classification and analysis, what we want to do is take a piece of text, and we want to do one of two things with it. We want to either say what the emotion is that the person was feeling when they wrote the text, or we want to get a general sense for how they felt when they wrote the text. Was it meant to be positive, or was it meant to be negative, or something else? In this talk, though, I'm not going to focus on detecting emotions. We're just going to talk about general sentiment. So is something positive, or is it something negative? Here's an example of some text that can be inspired by a positive emotion. So the sentence, "I love Justin Bieber," is kind of a sentence that appears here a lot. If you work here at Facebook, you know what I'm talking about. So the word love is probably, or at least statistically, probably speaking, meaning that this is a positively emotive sentence. But one thing that's interesting to note here is that the bigram Justin Bieber, a bigram being two words next to each other, could also have a sentiment of its own. We won't focus on that here. However, Justin Bieber could have a positive sentiment or a negative sentiment, depending on who's saying this. Now, this could depend on gender, it could depend on age group, and it could depend on geography. I'm not exactly sure what Canadians think of Justin Bieber, but we won't go there. Some text could also have a negative context. So I'm from Southern California, and I really hate the rain. So the word hate probably invokes negative sentiment. Now, of course, the word rain could also have its own sentiment related to it, depending on geography. For example, here in California, we're in the middle of a pretty large, bad drought right now, so the word rain could be positive. Whenever I hear the word rain, it's negative. It could also depend on the time also. It could be a temporal sentiment. So during an El Nino season, when we get a ton of rain, it could be a negative thing because of floods and all that type of stuff. Now, there's a couple of cases that I don't currently take into account, but they're very interesting to look at. One case is where a sentence has mixed emotion. So this is where you have two thoughts in one sentence, part of the sentence positive, part of it negative. So I really like the actors, but the plot was boring. So as is life, people are often very conflicted. This type of sentence is what I call a mixed sentence. And here, parsing the sentence can be more useful than just analyzing the words in the sentence. And finally, there's the case where text is not inspired by any sentiment or emotion. These are usually facts. Barack Obama is the 43rd president of the United States. And I remember I told myself I wanted to check that he's in fact the 43rd, but we're just going to go with that. And these are often called objective texts, whereas something that has sentimental notions is subjective. So now I'm going to talk a little bit about some current sentiment analysis approaches, both what we tried and general analysis methods. So some methods are based on dictionaries or are lexicon-based. Other methods are machine learning-based. Everything that's on this slide here is a lexicon-based method. CentiWordNet, CenticNet, WordNet Affect, and LIWC, which apparently is pronounced Luke, which is linguistic inquiry, and word count. So for my talk, I'm dividing these into two groups. There's a second group, and that is machine learning, or using a machine learning model for this. So you can use standard machine learning techniques such as SVM, naive Bayes, decision tree, whatever seems to work. And they're frequently used in a supervised setting. And the features that are typically used for these models are, say, the ratio of positive words to negative words, maybe the count of positive words and negative words, although a ratio is usually better. Or something more interesting are lexical features like quantifiers and negations. So in an English sentence, a negation is just the word no or not, which flips the sentiment of the sentence. Or you can have quantifiers, which are words like to or very, that either diminish or exaggerate the sentiment of the sentence. One method that's gained a lot of traction, or one piece of literature, I should say, that has gained a lot of traction, comes out of Stanford, as usual. And the author of this, Socher from Stanford, came up with this deep learning technique. So deep learning is kind of the hot new thing in machine learning. Everybody wants to use it. Everybody says they're using it. So Stanford, of course, is taking the lead. And they've created their own sentiment classifier that gets between 80% and 85% accuracy. And it combines bag of words. So if you're not familiar with that terminology, it means we just look at words. We don't look at anything else. The words that I'm saying are just a stream of consciousness, basically. That's a bag of words representation. But they also use lexical features. So they're using, for example, parsing the sentence into different clusters, depending on how the writer, author, or speaker intended it to be interpreted. The data that they use for this is called the Stanford Sentiment Tree Bank. It's hand-labeled by 3 human judges. So basically, these people took a bunch of sentences, and they diagrammed them out, and they had some list of features or some list of words that maps to a particular sentiment, positive or negative. Each atom, which is a word in this case, atoms could be other things as well, but we're gonna say they're words, or they are words in this research, and they're labeled with a positive sentiment, negative, or no sentiment at all. This graphic is basically what they do. So they divide the sentence into a tree structure, and each leaf node of this tree is a word in that sentence. So this full sentence is, this film doesn't care about cleverness, wit, or any other kind of intelligent humor. So some of these leaf nodes, some of these words have positive sentiment, some of them have no sentiment, and some are very positive. But when you bubble these words up into the parent node, there's a model that takes into account the lexical structure of the leaf nodes and how they combine to form a sentiment for that subtree of the sentence. And this is called the recursive neural network. They call their method a recursive neural tensor network. And really the reason why I mention this is just because it's kind of the hot literature right now, and I won't go into any further discussion about this method. This method is not particularly scalable. And data is scarce. So I believe they used something like 10,000 examples, and they had humans judge each sentence. Which gets me to my next point. Sentiment analysis is very difficult. And it's difficult for several reasons, and it also varies on the language we're talking about. People are complex, but so is the language that people use. An ideal sentiment analysis takes this structure into account. One classic example is the phrase, "this is not a very good day." There's a lot going on in the sentence, although our brains trivially determine what the sentence means, and that's a negative sentiment sentence. So although an ideal algorithm takes a sentence structure into account, we can do a pretty good job without it, and that's the point of the model in this talk that we'll discuss. So in the phrase, "this is not a very good day," for example, we have words like not, which induce nesting in the sentence. You need to know where the not part begins and where the not part ends. And this will flip the sentiment of whatever's within that nesting. So if you say, I'm not happy today, my car broke down, the phrase, happy today, my car broke down, Maybe because of the word happy, it may be determined to be positive, but the word not will flip that sentiment, which is something that a bag of words model can't really take into account by its nature. Words like very and to also exaggerate the sentiment. But also, and more difficult, is that some bigrams, like not very, are not very transparent. See what I did there? So as an example, I'm not very hungry. That doesn't mean it doesn't mean what it says, essentially. It's a softer form of I'm not hungry. Do you want to go to the bar? Well, I might say not really, but it means no, I don't. Some other things that are very difficult with sentiment analysis is that emotions may not translate across languages. So it's difficult to come up with an example of that, but for example, one example I'll use later is the word hot. So the word hot can mean I'm really warm, which is not really warm in here, or it could mean somebody that's very attractive. In the English language, that's true. In other languages, you might not have that distinction. Hot may only refer to a temperature. Also, sarcasm and humor are never handled well in an NLP system. There might be some research about this, but in general, you can't build a very good model that models humor or sarcasm. Also is the subjunctive mood. So English doesn't have much of a subjunctive mood. Other languages do. And you use a subjunctive mood to talk about things that you regret or things that you doubt or wishes, hopes, and whatnot. And that can sometimes be an issue in other languages. Not so much English, because we don't really have much of one anymore, or we don't have a verb conjugation for it. So now I'm going to talk about a first method that we tried. Now this method was done by my team before I arrived, and it was a pretty interesting method based on some prior research. So the first method that we did was from CentoWordNet. Now CentoWordNet uses what are called syn sets, which are meanings of words and they basically take words and they divide them into different meanings. They do some disambiguation for you in this corpus called WordNet. Which is available on the internet, and assigns to each word a score on positivity, negativity, and objectivity. So as you can see in this diagram here, we have 3 points on a triangle where we have a positive sense, a negative sense, and really a nonpolar sense. Now I believe there's also a model attached to CentoWordNet, which I believe uses a support vector machine. We didn't use that model, but instead we used the list of words to give the sentiment for each word. And then we use words like very and to amplify the sentiment, and words like not to flip it. And we devised our own scoring technique to handle this, and that ended up becoming the overall score. But there are problems with this method. Lexical analysis, such as we did, is very slow. So the lexical analysis method in CentoWordNet also involved part of speech, and part of speech tagging can be very slow. There are some that are faster. In Python, the one that we were using wasn't particularly ideal, and that's something we're going to revisit later. Lexical analysis is not very accurate. In this particular case, we had 65% accuracy, and our F1 score was 0.3. So an F1 score is basically a balance of precision and recall. Precision and recall are two metrics that come from information retrieval, and they give you more information than accuracy alone. F1 score goes from 0 to 1, so 0.3 is pretty bad. Additionally, human judges are very unreliable. There is some research that says that somewhere around when they were given a particular task, only about 20% of the time the human judges agreed with each other. So this is very problematic. And also, lexical analysis varies based on language. So our original technique did not work for languages other than English, because parts of speech are different and whatnot. But what if we use just words? What if we forget the lexical analysis part and just use words? This is a bit bold, but let's see if it works. What if we train a classifier instead? But where can we get label data to train this classifier? We came up with a better way. So one of the difficult things with working with text in a supervised fashion is that you need label data, and this is very hard to get. It must already exist. It has to be applicable to the domain that you're modeling. And if it doesn't exist, you need human labelers. One of the advantages of working at Facebook is that we have millions of labeled data points that come in every month, every day even. So, and the best part is they're already tagged by the person writing the text. So we know, so based on this, based on what they write, they label the text with how they feel. We don't have to guess it. We lose the ambiguity. So this is an example of some labeled data. When you write a post on Facebook, there's several different pieces of metadata that you can add to your post in addition to what you write. You can say where you are, you can say how you're feeling, which is what we'll use, or you can say other things like where are you currently eating lunch or something, or what are you eating. So here's an example post. I'm feeling blessed, blah, 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 and a picture. We also have the other categories of these type of things, as I mentioned. Where are you currently? What are you eating? What are you doing? We're only going to focus on emotions. We took these emotions, there's a lot of them, and divided them into 3 groups. And this was done by myself and one other person. So one possible way to improve this is to crowdsource it and also take people of different cultures and have them agree on what these set of emotions are. However, this is what we have right now. So positive emotions are emotions that are most likely positive. So I'm happy. We're going to assume that there's no negativity associated with the word happy. Although you can say I'm happy that somebody failed a test or something. We're going to ignore that edge case. Happy is usually a good thing. Blessed, pretty, these are all good emotions. And negative are probably negative emotions. So sad, angry, or ill. Then we have a lot of nonpolar emotions. And these are divided into several different categories. Hot, which I described earlier, could be a temperature or attractiveness rating, at least in English. Meh, MEH. Neutral, doesn't say anything. Or hungry. You could be positive or negative and be hungry. I'm hungry, my mom's making ribs, I can't wait. Or I haven't eaten all day, I'm really frustrated, and I'm hungry. That's not so good. We can take the text and turn it into a bag of words representation and wrap it up with the emotion, which in this case is blessed, and label it positive. Now we have our training data. So our experiment, some of our results for some of the description for our data set for our experiments is we worked with 90 days of data at a time, and we have millions of pieces of English content that contain text tagged with a positive or negative emotion. For now, we're ignoring the nonpolar emotions. We're only going to do positive or negative. And millions of total unique words can be used as features. So there's some pruning that gets involved here because you have a lot of words that people make up. You have a lot of misspellings. Those kind of get filtered out statistically, fortunately. And for version 1, our goal is to classify text as either positive or negative. Technically speaking, we're detecting positivity. So one of the things that you have to do as a machine learning person is feature selection. So one thing that we tried, or one thing that we do is chi-squared feature selection. So we in features where n is in the millions, maybe too many. So we use chi-squared to reduce this to the top k features. And for our first version, it was in the thousands range, and then we raised it to the millions range. And we took features that had confidence over 95% or a p-value less than 0.05. And took the top k features of that set. Now there's a better way to do this, and we're probably going to work on this, is to use the hashing trick, which you just hash a bunch of words. They all map to the same space. You know the size of that feature set then. You don't have to worry about how many features am I going to choose. You don't have to worry about how many megabytes or gigabytes of RAM you're using because it's fixed with the hashing trick. This also scales well with pandas across multiple cores. The model itself, is multinomial naive Bayes. Now, naive Bayes has been criticized as the punching bag of all classifiers. It's the model you use when you're just starting, and you just want to see, is there any type of signal here? However, what's very strong about naive Bayes is that it works in many cases. It's still not quite known why it works in many cases, but one of the assumptions about naive Bayes is that all the features are independent. In language, this fails miserably, but miraculously, it still works pretty well. So if you're not familiar with the nomenclature on the screen, basically we have a class C, which is positive, and we have a vector F, which contains feature counts, and we want to compute the product of the probability of seeing a particular feature given that it's in the positive class. Multiply all those together and divide by the prior, which is the probability of a particular piece of text being part of the positive class without any other knowledge. It's really a normalization constant. Then we classify, we're going to get a probability out of this, and we classify. So if we have more than 60% confidence that this is positive, we label it positive. Less than 40% approximately, we label the text negative. If it's somewhere in the middle, we have to do some more processing. We're going to say we don't know if it's positive or negative. Now, there's a better way to do this, and it's to create 3 different classifiers, maybe 2. A positive classifier and a negative classifier, and have some ensemble of those 2, which is something that we'll probably do later in another version. The best part of this approach, using bag of words and not using the lexical features, is that it works for multiple languages. Currently, we support English, Spanish, Portuguese, Italian, French, German, and Turkish. And we want to add Asian languages because those are very important as well. We also want to look at, is there a difference between different locales, such as American English versus British English is very different. And also emotions do not translate well, so that's something that we need to visit as well. So before I go into the code and the architecture and how this actually runs, I want to give some results, which is of course necessary for any machine learning task. So based on all the languages you have, our accuracy is between 77 and 83%. I showed earlier that our accuracy was, not our accuracy, that Stanford had an accuracy of between 80 and 85%. And that's kind of the state of the art right now. So we're not doing too bad. Now, this is a range because it depends on the data used, and it also depends on the particular language. English is about somewhere in the middle. And our F1 score is between 0.79 and 0.84, which again ranges from 0 to 1, so it's very high. We also have our false positive rate, which varies a lot depending on language, and goes from 7 to 22% and 9 to 24%. And for reference, the original classifier that we trained had 65% accuracy and an F1 score of only 0.3. So this is a huge improvement. So some of you might be machine learning geeks, but this is absolutely necessary, is to have the ROT curve. So basically, when you get a probability out of naive Bayes, you would assume that, well, if the probability is greater than 0.5, I'm going to label it as part of the positive class. That's not always the best thing to do, though, especially if you have imbalanced data. So what the ROT curve does is it takes a bunch of different thresholds, not just 0.5, and computes the false positive rate and true positive rate and plots them on one plot. In the absolute worst case, we would get a model that's along the diagonal line, which means chance. A great model is going to kind of go up the y-axis and across the x-axis, which we never see. So this is pretty good. And as you can see, certain languages do better than others. So French and Italian are kind of the weakest, and Turkish, miraculously, I don't know Turkish at all, performs the best. And apparently, a wise person told me that Turkish is apparently easy to parse, but I don't know it, so I have no idea. Oh, perfect. That makes my job a lot easier. Also, the precision recall curve is another thing to look at. I won't say too much about this, except that the ideal case is where you have a horizontal line at precision equals 1.0. So this is pretty good. So we're at PyData. We want to hear about the Python behind this. So what do we use for this? We use several technologies that are either released or that we're talking about here at the conference, and that's Hive, Presto, and DataSwarm. DataSwarm you'll hear more about tomorrow from Mike Starr. He'll give a talk about that, and it's a Python-based way to develop data pipelines. And that's how we get our data. Then we use Pandas for managing relational data from start to end. It gives us a nice data frame format, similar to the data frame in R. We use Scikit-learn, of course, for the text processing and machine learning, and we also use NLTK in the early stages. NumPy under the hood, of course. All of these are based on NumPy in some way. And we use SciPy under the hood for working with sparse matrices. Also under the hood in Scikit-learn. Pandas provides several things for our use case. It provides simple tabular data structures, just like in our data frame. It provides fast row and column-based operations based on NumPy. The data structures are nearly interchangeable with NumPy arrays, so you can use them with Scikit-learn very easily without any or much tinkering. And it has easy I/O for debugging, very easy to read-write to a database or to print to a CSV file. The database support, I believe, is experimental, but it seems to be getting better. Wes McKinney recently came and spoke, and one of the things that he mentioned was that maybe pandas may not be performant for like high-frequency trading. That's not our use case. However, we found that it scales very well for our use case. So that's very very powerful for us. Scikit-learn provides a uniform interface for training many kinds of models. And I'll point to this in the source code. It's very easy to switch models and experiment with different things. Back in the old days, before I used Scikit-learn, I would usually prototype a model in Weka, which is Java. I'm not going to say too much about Weka, but you can use that to experiment with different kinds of models and then implement them in Python. It's very easy to do that with Scikit-learn, though. Powerful and fast vectorization of text. And it supports, this is really important, critical for us. It supports incremental training as of 14.1. I believe we're on 15 something, maybe even 16 now. But 14.1 allows you to train an increment, which means you get a batch, train a model, get another batch, and you can add that to your current model, and you keep doing this. And it makes processing very scalable. Now I'm going to switch gears a little bit and describe some code. It looks like I have plenty of time about how to write and diagnose a classifier. So let's see if I can do this without screwing this up. Okay, perfect. Spoke too soon. Okay. So the code for this is very short, as you can see. And that's one of the beauties of Scikit-learn. Now, obviously, in our system, it's much more complicated because there's a lot of infrastructure behind this. And probably only 5% of my job is on the screen. Less than 5%. So first, we read in data with pandas. And this is some movie rating data, and that's split on a tab space. And then we have this easy function that, actually I probably shouldn't scroll with the screen so you can see the whole thing. In the cross-validation module, we have a train test split function that lets you set the training size or the testing size as some proportion of the full text. And this returns you two data sets, a training set and a testing set. Now, if you're using something like a support vector machine, where you have a C and a gamma parameter to tune, you might want to also have a validation set. Then I vectorize the text. Vectorizing basically means I take the bag of words and I convert it into a vector that's standardized across all of the text in the corpus. This is a huge pain in the butt if you don't do it this way. I've had to do that and it was very painful. So you're going to get basically a very sparse vector or matrix from this. And this is what the vectorizer does. It also removes stop words, and it gives you a count. There's other types of vectorizers you can use as well. Then I'm going to, so below in this comment, I'm not going to actually do it, or I'm not going to actually use that as part of my demonstration, but there's a lot of other powerful parameters that you can pass this function. You can analyze n-grams instead of just words. You can set the minimum number of times a word appears, but in order for it to be included. You can also set the maximum proportion of documents that the word's included in as a ad hoc form of stop word removal. Then next we're going to train. We're going to fit a transform, essentially is what it's called in the Scikit-learn nomenclature, on the training data, which is now, which is a data frame. There might be an error there. And then we're going to use that. Here we're vectorizing the text. I'm sorry. I'm getting ahead of myself. So here we're going to vectorize the text. We're going to train the vectorizer. In other words, we're going to give different columns for each word in the lexicon. And then we're going to get a test matrix, which uses the same columns. The beauty of this is that's automatically going to drop words that do not appear in the training data. So this is another pain if you have to do this manually. So you have to worry about what words you use in the training data that do not appear in the test data and have to deal with that mess. Then I'm going to take the original data. So I add a little wrinkle in here. The data is originally coded as post and neg. Instead of doing that, I'm going to, instead of using that, I'm going to convert it into 0 or 1 with a simple logic here. Then I'm going to set up a multinomial naive Bayes model. Now the beauty here is if I want to change the type of model I use, all I need to do is replace this with a comparable model. So for example, logistic regression and maybe SGD classifier will work here. Some other ones may not. You may need some more parameters or whatnot. And then finally, I'm going to fit the model. I'm going to fit the model on the training data, as well as on the training matrix, as well as the labels for each point. Now with the test matrix, this is data that I want to classify, not train. So now I want to classify some text. I pass in the test matrix, and I call the predict function on it. And this is going to give me back a vector of predicted sentiments. And I also want to get the vector of predicted probabilities. This is how I'm going to threshold, and it's also how I create the ROC curves. And the predict function will give you back the predictions. The predict proba function will give you back the probabilities, which is really nice. And then finally, you have to, of course, diagnose your classifier. The first thing that you want to do is get, say, an accuracy score. So you get an accuracy score using the score function, and all you do is you give it the test matrix, and you give it the known labels for those test cases. And then you can compute the precision recall and F1 score using this nice function, precision recall F score support. Now, what's beautiful about this is that computing a ROC curve manually, it's not too bad. However, I tried it, and it took about 45 minutes to iterate over all the languages and iterate through all the data. Instead, I simply use this built-in function that gives me back my different error rates that I can use to compute the ROC score. And all I do is I iterate over the languages. And it took me from 45 minutes to maybe 10 seconds. I'm probably going to, I won't go over the matplotlib part because this was used to create the graphics, and it requires a particular data set that I can't release. I might go through it if I have time, just to give you a flavor for what matplotlib looks like, but it's not a critical part of my talk. And if I do post the code, you'll be able to apply this to any type of data set you might need. But this just shows that in IPython Notebook, I can run this code, and it will give me back a nice ROC curve and a nice precision recall curve. Okay, so that's the hard part, because it requires me switching, context switching here. So now we're going to talk about the system architecture, about how we get this to work at Facebook. Basically, we start with a bunch of data, of course, and it comes from a data swarm pipeline that we're going to assume lives in the clouds. It lives somewhere. And this gives us a training and testing data. We're going to take the full data and split it into a training and testing set. 70-30, you can experiment with this. Some people like 75. 50-50 is probably not advisable, but I've seen people do it. Then we're going to do feature selection, then train on the data. That's going to give us a model. The model can then be pickled, or it can be dumped to disk with joblib, which is an external package within Scikit-learn. And sometimes gives you multiple files, but they're read in, they work beautifully. Then we're going to test the model using the holdout set, and then we dump this data either to MySQL for more diagnostics or for dashboarding. So what we currently have is based on this, is a Hive transformer. So I'm not a Hive expert, but what a Hive transformer does is just some script that reads from standard in and writes the standard out, and it essentially transforms the data in some way. So we're able to write back to Hive or write back to some other data store. We also have a Thrift client, or a Thrift server, I should say, that provides on-demand classification, and a command line client for analysts that want to do one-off jobs, small one-off jobs. So basically the point of the talk was the following things. With a ton of self-labeled data and a very basic algorithm, naive Bayes is as simple as it gets, we eliminate the need for lexical parsing and can process multiple languages. This is very scalable and provides us a lot of flexibility for the future. The text author is the best judge of his or her own feelings rather than a set of other human beings. PyData infrastructure like Pandas, Scikit-learn, NumPy, SciPy, and Matplotlib provide powerful and production-level science and computing. So maybe if you're doing high-frequency trading where there's a lot of money at stake, maybe you may not want to, you might find an issue with some of these, but for our use case, it's been very good. It's been a very strong friend to have. So this concludes what I had to say about sentiment classification here at Facebook. I'm now happy to open the floor to any questions you may have.
Hi, I have a couple questions real quick.
Okay.
So the first one was, I noticed that you were basically using user labeled data, except when I check in on Facebook, I can create my own emotions. And I wanted to know how you use that. And then another one, slightly more technical, is you mentioned you use chi-squared. I didn't know if you used univariate or multivariate. And if you use univariate, how do you handle feature correlations?
So to answer the first question, which was you can create your own emotion, we only take the common set of emotions for this particular use case. Maybe we'll work with custom ones later, but we have a set of emotions that that we can readily use. To your second question about using chi-squared, chi-squared is by nature a double-sided test statistic. And I actually tried odds ratio, which is a one-sided statistic, and found that it didn't give very good results, or feature selection accuracy wasn't very good. However, I do see the need to use a one-sided statistic. However, for this particular classifier, it predicted positivity. So double-sided was okay in our case. If we wanted to have a positive and negative classifier, we would have to use single-sided. I did make the mistake of trying a double-sided classifier on a positive and negative classifier, and you basically get the same results, or I should say opposite results, but using the same basic measures. Oh.
Sorry.
Yeah, I have one. Just real quick, did you do any kind of like word stemming for this?
So that's a good question, and there's a debate about stemming and whether or not it's useful and what it's useful for. A lot of textbooks say that you should always stem the data or stem the words. I personally don't do that. I think in this particular case, it's helpful to not do that, especially for other languages where you have different verb conjugations. Certain words, like past participles, might have different meanings than, for example, the present indicative. So I don't stem. It would reduce the feature set dramatically, but I haven't found it to be very useful. That's kind of just an engineering decision. I haven't tested it though, but I'd be interested in testing that.
So far, you've been looking at single author text.
Yeah.
Have you looked at conversations? Have you been thinking about that, where you have two parties involved?
We haven't really thought of that. We've only been using single author.
Of all the, sorry, you guys said that you limited the texts that you were analyzing to ones that had emoticons so that you could be sure about that when you set up your training. What percentage do you think of all the texts use the emoticon? So I'm curious, like, what percentage of the data are you actually, using for your training if you look at it in like the big picture?
That is probably something that somebody else would have to answer. I'm not actually sure what the actual proportion is. Somebody who deals specifically with that product would probably know the answer to that.
You've shown two methods that you try. Did you try to make them compete and see which one of them works better when? Like on what kind of...
Is it always better or is it only better some of the time?
Yeah, sometimes some...
Honestly, we haven't. Basically, we looked at the judgments. A few of us looked at the judgments that came from the original classifier and then the new classifier, and it was obvious which one was better. There may be cases, and I do suspect there are cases, where lexicon base is better than bag of words. But for this particular work, we didn't worry about that case.
For what you just mentioned, for looking at judgments or generically debugging, if you're looking at specific examples of mistakes, I hope you don't have the ability to look at random private Facebook posts. So I was wondering, what do you look at?
These are public posts.
Hey, so how does this problem change when you're trying to predict the actual state? So feeling blessed versus feeling happy versus feeling sad versus feeling frustrated.
The problem gets a lot more complicated, and I haven't had much time to delve much into it because we've been building this infrastructure, but it's very complicated, and what I found very ad hoc is that some emotions are much easier to predict than others. Then you really get into the case of sarcasm, humor, cases where people don't say very much, there's not much signal there, but they have an emotion. That might be something that we look into, but right now I don't have too much to say about that, unfortunately.
Once you have the trained model, a model for English, what ended up being some of the features, some of the words or bigrams with the highest weights?
So one thing that we had to eliminate first was all the original emotions. So it's trivial that the most important features would be happy or sad or blessed. We had to remove those. Some of them were things like birthday, church was one, God was another one, because a lot of people might use blessed, and those are kind of correlated with each other. I'm trying to think of some of the other ones. Ill, I believe sick, not ill. Sick was one of them. There was probably a list of about 10 that were very high. Those are just some of them.
Did you get the, I'm sorry if you said this, did you get the same sort of accuracy results on the Facebook posts or the sort of traditional language WordNet set of corpus? You know, like has the language changed in a sense so that you get different sentiment or a more modern corpus than the old?
Oh yeah,
corpus?
I mean, you might see things like YOLO. I mean, that's not in a dictionary.
But,
maybe
it
is now.
Did you get different metrics, different scores? I mean, did you get different precision, different recall, different accuracy?
Well, we use bag of word approach. Are you talking about the original method?
No, your method, but on different corpus, like your Facebook corpus and the old WordNet corpus. Would they give you the same?
Oh, so the original model wasn't tested on the original WordNet corpus. It was tested on Facebook public posts.
So,
does that answer your question?
No, but I'll ask you later.
Okay.
I had a follow-up question on someone over there asked if you basically looked at your features that your model selected as the most important for each sentiment, and that made me think of your earlier slide when you highlighted certain words like love, hate as being generally strongly positive or strongly negative. Did you experiment with using those words in your actual features? Like if you'd see that word in a piece of text, mark it in your feature vector.
Oh yeah, some of those
positive.
words were I love is a top feature.
Okay.
I don't know if I mentioned that, but a lot of the obvious words were in the top feature list.
But I mean, did you sort of try to boost your classifier by having like a dictionary lookup for each input and saying, oh, I found this many occurrences of love, so I'm gonna have a column for how many times I see love?
Not for the current incarnation, no.
So can you talk right up front here? So.
Talk here?
Yeah, right here.
Oh, right.
I just was going to ask, can you give us a sense of, since this is like a machine learning problem, pretty much all in memory, how big was the server, how many features, how many columns you used? Because you didn't do this in a distributed fashion, right? You had like one big machine to pump all this data through, right?
Yeah, I can't answer specifics about like the size of the server or whatnot, but range.
It was one server. It wasn't a distributed.
I can't answer if it was multiple servers or one, but what I can say is that the number of features was originally in the thousands, and then moved to the millions, and we got better accuracy that way.
But it was on Scikit-learn, right? That's what.
Yeah.
Okay.
Yeah.
Hey, did you grid search your count vectorizer parameters at all? Here. Did you? Because did you look at a couple of different n-gram ranges and whether or not to take out your stop words?
So n-grams is something that is not in this current incarnation, and it's something that needs to be.
Okay, so, but I mean crucially not character n-grams, but word n-grams.
Word n-grams.
So you're just doing unigrams?
Just using one word,
okay.
Yeah.
Okay.
This is only on unigrams, which is a big limitation right now. We think we'll get an even bigger boost by using bigrams especially, maybe trigrams.
So Professor Chris Potts at Stanford has a really classic example about contextuality. So for instance, if you say a movie is predictable, that's bad. But if an electronic device or safety device is predictable, that's good.
Yeah.
How are you dealing with context?
That's a very, very difficult problem, and it's definitely something that is worth looking into. This classifier only treats everything globally.
Have you tried running this through Vopal Babbitt? Oh, right here. Did you try running this through Vopal Babbitt? Any idea on how
running it through what?
Oh, Vopal Babbitt?
No, but I do like Vopal Rabbit. So, and the point of this talk is to talk about Python. But yeah, that's worth trying too.
Yeah, following up on his question, how do you deal with the phrases with the generic words like the F word, where you can express pretty much everything with the F word?
Yeah.
Right?
So the beauty of some of these approaches that we're using this is that word appears so many times positively and so many times negatively that it's a wash. It's not a feature because it doesn't give us any information. It's context specific, so I mean, it depends, but on a global scale, it's not a feature.
So with your bag of words, how do you handle negations, like not?
We didn't. That's the beauty of bag of words, is that there's no lexical structure, and we were still able to do pretty good. I would like to incorporate that somehow. But for this particular this particular project, it was just a bag of words approach. I do think that might give us even more accuracy, but it's also a lot more complicated and less scalable.
For like LOL, like laughing out loud, stuff like that, acronyms, did you guys translate them into individual words for classifier?
No, LOL is just LOL. It's treated as LOL, as a token.
It's going to get out into dictionary.
Behind that, 3 rows, center of the right.
So someone asked you earlier and you couldn't respond as to what percentage of like total posts had tags. But I'm curious if you have a heuristic about what words never get tagged with an emotion, and are those things that don't have emotions? Like if you post that you're in the grocery store and you're buying lettuce, like maybe you don't have an emotion about that. But
that's interesting. I haven't thought about that. That's a pretty good point. I mean, my assumption is that every word at some point, this is a very naive assumption, but is that every word has at some point been tagged with an emotion across billions of users, but that could very well be wrong, and I haven't looked at that.
yeah, it's just like, for example, posting that you're with your loved one watching a movie, pretty commonly going to have a tag, but if you're posting about some complex political issue, like probably not going to come up that you're tagging anyone.
Yeah, that's interesting. I mean, for this particular classifier, it'll drop out, but I am wondering if there are words that have never been tagged.
Okay, begging the question, what's the use of it?
So this was a hackathon project, and NLP is something that I'm really passionate about, and I thought it was something that was very interesting to try. And we're always looking at new variables and ways to make the Facebook user experience better. At this time, I'm not the person to answer how it would be used, but we have the infrastructure for it.
You said you use millions of features, so how sparse was your matrix?
Very. Anything with text is always very.
I mean, any number, did you even go through it?
I can't give you a number. The assumption is that when working with text, it's always going to be very sparse. Okay. There is things you could do, like running LDA or some type of cluster on the data before training a model, and that's something that I'd like to try, and then, of course, it won't be as sparse, and then I would have a number for you, but it's trivially sparse.
So you might have already mentioned this before. Have you thought about including other activities that might indicate emotions, such as, and I guess this would be going forward and expanding on it, so checking in a particular location, or uploading photos along with the actual post, or even doing certain activities like watching a movie that could indicate?
So for this particular project, we're just looking at emotions. That would beg a particular use case, which I don't know about yet, or if there is one. Oh,
yeah, I was wondering if you had experimented with handling misspelled words, like maybe looking at character n-grams, throwing out character n-grams that had occurred too frequently by TF-IDF, and just trying to match that, and also sort of reduce the sparsity that way.
That's a really fun problem. Not for this particular incarnation. Maybe some later work. I've worked on it at a previous company and really enjoyed it. But that's not handled in this particular incarnation. They would probably just be dropped out, especially if it's a common misspelling, like the word commitment, that's a feature and it's so commonly used. It'll probably show up as a feature as well as the correct spelling. But things that are rarely, someone doesn't know how to spell the word dog, for goodness sakes, that's probably going to be dropped out. So the question was, is the reason why English may not have been as predictable as, say, Turkish, is that so many people that are on Facebook may be second learners of English?
Did you control for demographics, basically?
No, this was just total global analysis. That would again beg for a particular use case. Then we might do that, but not for this particular work. But it's a good suggestion, and it's something that we would look at if we were to. Yeah. Thank you. Thank you for coming.